Welcome to day 25, and today we're going to be talking about something a little bit different. We've been doing a lot of codey things lately, and so you know how to write a bunch of code. You can represent objects in real life with code inside, with the code, with classes and instances. You can make a bunch of functions, but we've been talking it's been kind of hidden in, our 30 days, but what makes one version of code better than another? Like if I say your code's better than my code, like how can you say that? I mean, everyone can code differently, right? So they're all versions of art. Well, kind of. What makes code really good? One thing is efficiency. If you have this big thing of data and you need to process it, and one version, like one way to do the code takes only 10 minutes to run, and another version of the code takes like 10 hours to process, then you would say the first version is better because it's faster. Now, just because it's faster, of course, doesn't mean the first version is necessarily better, but it's one thing you could look at. Consider space. If one version of the code, takes up half the space on your computer and another version takes up only like a tiny little bit thing, then the second version would appear better. But what if the version that takes up more space runs faster and the version that takes up less space runs slower? Who's the winner there? And what about the elegance of code? Does that even matter? Does it matter if it's very easy to read and understandable and makes sense? Well, this is what we call the space-time trade-off, where you can either optimize your code to use less space or to run faster. Usually it's going to be a mix of the two where you are going to be using a lot of space, but it may be a lot faster, or you'll be using like no space at all and it'll be kind of slow. As programmers, usually we're looking to optimize speed. We want to make our computers fast and run as quickly as possible because nowadays, space is very available. We have Dropbox, Google Drive, OneDrive. We have all of these drives that we can do and things. And so space isn't really a factor anymore, but it could be a considerable factor depending on what you are programming. And elegance, as for all beautiful things in the world, it is wished for, but not necessary. Really, though, it's really wished for. You want to have this awesome algorithm that runs super quickly, and it is incredibly elegant. That is the goal here. And obviously, it's preferred, but if something runs faster, then you're going to choose that over the other thing. Now, how do we know if one version of code is faster than another? That's what we want, right? Well, we could start a timer and have them both run at the same time and see which, algorithm finishes first, but we can actually just look at the code and figure out what's going on and which one is faster depending on what the code looks like. How do we do this? Well, I'm going to show you with the wonderful NetBeans. And so we will go up here, we will type NetBeans, and this will load up for us. And we are just going to create like a simple runtime, because that's what we're talking about here. When we're talking about like how fast applications run or how fast programs run, we're talking about the running time of them. How fast do they run? It's just a, vocabulary word thing. And so we are just going to do a new project here. And it's going to be a Java application, and we are just going to call this runtime practice. You could call this algo practice, I'm saving it on my desktop. And it's loading up, it's over here, it's great, there it is. And so in this, we're going to create a couple of algorithms that are going to kind of prove to you, if you don't think some algorithms are faster than others, but then can do the same thing, well, I'm gonna prove you wrong. And so the first thing that we're going to do is inside of our main, we're actually going to set a timer so you can actually see like what the cycle time of all of this stuff. And so we are going to do a long start time equals system dot current time mils, and that's just going to get like what is the current time according to the system. And then we are going to have our program thing in here, and then we are going to say long end time equals system dot current time mils. And then we are just going to get the difference of this, and we are going to say long duration equals end time minus start time. And then, of course, we're just going to print out that duration. And so we are going to create a couple functions, and we're going to do this thing on each of them. And so we'll do a println, and there we go. And then inside of here, we will say test, and then we'll say plus duration. And so one function, we're just going to kind of make some functions for fun and then see if we can optimize them to make them run faster. And so the first function that we're going to create, and all of these are going to be static because it's just, a little practice thing, and we are just going to create a repetition function. And so if you're given a string S and you say it's like A, B, C, A. And so inside of the string, if you say, okay, I have the string, how many times is A in it? Well, if it's A, B, C, A is in it twice. And then you could call the function again with A, B, C, A with C, and so C is in it once. And so that's what we would want our program to do. And so we will do a public static, and we're going to want to return this int, how many times is it repeated, and we are going to call this function find number of repetitions. And we're going to do things inside of here. And so we're going to have to keep track of a sum, which is going to be like, okay, how many repetitions we have. And we're going to have to go through each character in the string to see, oh, is this equal to the character? And is it counted as a repetition for each single one? And so, of course, I forgot to add our string S in here and our string S and our character C. And so for each character in the string, we want to see if it's equal to the character. And if so, then we want to add one to the sum. And so this sounds like a simple for loop operation here. And we will say for int I equals 0 all the way up to S, well, S is less than S.length. Then we want to increment I. And then when we're doing this, we want to check if the character at I is equal to C, and if it is, then we want to increment the sum, and then at the very end we are just going to return the sum. And so this is a function that does things. It does things, and so we can see how long this function runs for like a simple thing if we just say find number of repetitions, and I can't ever spell anything correctly, and so repetitions. And of course, we need to add some parameters here. And so I'm just going to add the string A, B, C, A, and we will say A is the thing. And so this should return 2. And so we are actually going to system.out.println this thing and see if it works for us. And A, I need to put that in single quotes because we want it to accept a character. And so we'll press play, and it's going to run. So here we had 2 as our answer, and that's good because there were 2 A's in there. And then we had 2 here because it took 2 milliseconds. And then we'll add this little milliseconds thing so that we know it's in milliseconds. And so here it took 1 millisecond. If I run it again, it takes 0 milliseconds. Like it's a very fast function. And it might depend based on different resources that are available if it runs faster at a different time or not. And so yeah, there we go. And so it was 1 millisecond, like super fast, super quick. And it didn't really matter there. But what would you say the running time of this function is? You don't want to just say it's 1 second. Like our input here was pretty small. What if it got larger? What if it was a bunch of little characters here and we don't know what they are and they're a really long thing right there. Okay. Now if we try to run it, how long is it going to take? Okay. Well, that's not a good example, but it could be infinitely characters long. And so we're just going to kind of delete all of this. But 18, and I bet you that is correct, but I don't really know. But yeah, if your string is really long, then it could potentially get to a high running time. But what does that even mean? It just takes a really long time to run. How do we even know how fast a function goes? Well, we can look at the runtime complexity of it. What's that? Well, we ask how fast is this function based on its input, on the size of its input, n. In other words, we try to find out like how fast the code runs in proportion to its input. And so if its input is really big, like say the input is 100, like does it run for 200 milliseconds or will it run for 100 milliseconds or will it be like half that? Like what is that proportion there? And that's how we're going to compare it to other functions. And so if I give one version of the code a string of 100 characters and another one the same string of 100 characters, and it takes 1 second for one of the functions to do it and 10 seconds for the other function to do it, then you could say the one that took 1 second was a lot faster and therefore better, because as computer scientists and programmers, we're looking for super fast code. And so I talked about proportions and things, and now I'm actually going to give you some real computer science notation. And so we kind of categorize this into 4 running types. And so they're like 4 categories that we put our functions into to describe how fast they run according to their input. And so the first running time, I guess you could say, is O1. And I'll talk about the O a little bit later, but 1 means constant. And so it takes a constant amount of time to run it meaning it does not depend on the input. So the input could be 1,000 characters long, and this thing is only going to be run like once or twice. It's not going to be anywhere near the size of this infinite input. It's just going to be constant. Logarithmic, that's like taking the logarithm. The logarithms to say you have 16. If you divide that by 2, you get 8. Divide that by 2, you get 4. Divide that by 2, you get 2. And so that's like 3 divisions. Oh, I hope I'm right on that. Okay, it's like 3 divisions. And so like the log of 16 is 3, but like the log of a really high number can still be 4. And so that's also a way that you can represent the things. And so if you have a super high input and the logarithm of that is like, I don't know, 20 or something, then it only takes like 20 milliseconds to run or something like that. And even though you have this really big input. So constant is like super, super fast. Logarithmic is like the second best. And then the third best you can get is linear, meaning you have to go through each element once. And so here inside of our find nums of repetitions, we had to go through, in this for loop, we had to go through each like entry of the string. So each character of the string. So if your string was 1,000 characters long, you need to go and you need to check a condition for each of those 1,000 characters in order to find out like your answer. And you have to do that because of the way the function is. And so sometimes you're not going to be able to get it down to constant or logarithmic time. And that's okay because some functions require more stuff. But usually you want to try to get it down to linear time because that is like the key. That's what we want. If the size of the problem is equal to the size of the solution, we're doing pretty good. And so the last, category you could say is quadratic. And so you have right now constant, logarithmic, linear, and now quadratic time. And that basically means you have to go through your input like once and then, another n times. In comparison to Java code, it means like you kind of have an outer loop and then an inner loop, and that's how you get the n squared, because for each thing that's in the outer loop, you have to do a whole nother inner loop. Hence the n squared. And so if we analyze this, find nums right here, like I said, this for loop is going to be in linear time. It's going to be in n time because we have to check each character inside of the string in comparison to which character that we enter as our second parameter. And so anything inside the for loop is going to take n time-ish, very close to n time. And then this n sum, this declaration, we only do it once, and it's constant because we're always going to do it no matter what the input is, and it's just a simple thing. Returning, again, that's going to be constant time. But inside of this for loop, this for will actually get executed n plus 1 times because we're going to have to execute it once to find out, oh, the condition isn't true, so we should go to the sum. So this top part will be executed n plus 1 times, but this if statement will only be executed n times, and same with the sum. However, if we want to be super specific inside of this like for loop thing, this int I equals 0 will be executed only 1 time. It'll be constant time. This condition is really the thing that's going to be executed n plus 1 times, and then of course this addition is going to be executed only n times, and then everything of course inside the for loop is executed n times. And since these are constant, it's just n. If they did something else that was not constant, then it would be n times whatever was doing the things in there. And so we will talk about that later. Moving on, we are going to actually create 2 versions of our next function. And this is where you're going to kind of see the running time difference and put it to practice. And so if we do public static int find nums of repetitions v1, and this is going to take a string s, and instead of a single char, we're going to create an array of chars, and we're going to say for each thing in this array, for each character in this array, how many times is it in our string? And so to do this, it seems pretty obvious to do a brute force solution, and we'll talk about what that means in a minute. And so if we do an array list of integers, and this is just going to be our sums, and it's going to be a new array list, and this is just going to hold all of the sums for each of our chars. And it doesn't have to be an array list, it could be an array, but we probably should make this an array. So we will do an int array, and this should actually return an int array as well. And so we'll have this int array sums, and it should be exactly as long as our character array because that's how many sums we want to return. We want to return the sums of each character inside of our character array. So we'll do c dot size length. Yeah, and so there we go. And then we want to say for int I equals 0 again, while I is s.length. Less than s.length, then we will increment I, and then we will have this if statement in here. But of course, we don't need to just check it for a single c, we need to check it for all of the characters in our char. So we'll say for int j equals 0, j is less than s.length, and this will actually be char c.length. Then we'll do j++, and for each, so this says for each character in the string, I want to check for each character inside of our character array. So say k is the first thing inside of our string, and inside of our character array we have L, M, K. Then for k, we want to check if it's equal to L, if it's equal to M, or if it's equal to K. And so this is like the essence of a quadratic, n squared running time, because we're doing for each thing in our string, then we're going to do, we have to check it for each thing in our character. And it won't be exactly n squared, which I'll talk about in a second. But yeah, let's just finish this function. And so if we want to say if the character at I inside of our string is equal to whatever is at j inside of our character thing, then we want to increment the sum that's at that index inside of our sums. And so we'll say sums at j equals sums at j plus 1. And because we use this constructor, everything inside of this int sums is going to start off at 0. So this is going to be safe here. And then at the very end, of course, we're going to just return our sums. So like I was saying before, this is called a brute force solution because we check every possible outcome that could possibly happen. For each thing inside of the string, we compare it with every character inside of our character array, even when it's not needed. And so say we already found the character that it matches up with, we still check the rest of the characters. And so it seems that this can be optimized a bit more. So looking at the running time of this algorithm, what do you think it is? Well, this first line is going to be constant, so it's going to be 1 time. This next line is going to go for, say, n plus, it depends on where it is, but the first thing would go for constant time because you're just setting I equal to something. This middle thing would be equal to n plus 1 because we're saying n, like I keep saying n is the length of the string, it's the length of our input, it's the size of our input. And so if it's, 100 characters long, then n would be 100, and you could calculate that running time, or the essence of it in comparison to other versions of the code of the function, such like that. Okay, so for this middle condition, we do n plus 1 because we have to check and make it fall out of the for loop, and then this incrementation only happens n times. And so what about this inside loop here? That's really weird. So well, no matter what, everything in it is going to happen n times because it's inside of this for loop. But how many other times? Well, this j thing is going to happen once for every iteration of this, outer for loop, and so we'll have n time. And then for this for loop, it's going to be executed as long as the character is, and so we'll say the length of the character array is m. So we'll say n times m times, because for every character inside of the string, we have to check every single character inside of our character array. So that's why we have this n times m. We have to go through the entire string, and at each instance we have to do, this character thing. And then for this last thing, we have to do n times m as well, and this will actually be a plus 1 because you have the condition that you have to check here. So yeah, but again, this is where it gets kind of nitty gritty because now our running time's getting bad. So inside of here, what will it be? Well, it'll be an n times m thing again, an n times m thing again, because you're doing it first for the n times. So say the string is like 5, then in your character array is 5. Then for each character inside of this string that has 5 things of it, so 5 times you're going to have to run this whole thing, but then inside our character array is also size 5. And so this will also be run 5 times for each character in the string, and so this will really be run 25 times, and that's how we get this n times m. Now the character array and the string, don't have to be the same size, which is why we have this n times m. We don't have n times n or m times n. We have the n times m because they could be different lengths, but they could also be equal lengths. And so what is the running time of this? Well, this last line is just going to be, constant. And we find the running time by finding the dominant operation. And so that just means the operation that takes up the most amount of time. So up here in our find num of repetitions, we had this constant time here. We have this 1, n plus 1, n, and then we have this n as well, and then we have this as n, and then we have this as just constant time. And so what is the biggest thing out of this? Well, n plus 1, and then inside of n plus 1, the big thing is n, and so that's what makes this linear time O(n) time. And I'll talk about that O(n) in a second. And then down here, our dominant operation here is the n times m, and so we will say kind of quadratic, but more like multiplicative, but we will say quadratic time, and this will just be O(n) times m. And so what does this O mean? Well, it is O notation, and it means that how long the algorithm takes is never going to be greater than n. And so say, like in this first thing, say our string has 100 characters, it's never going to take over 100 time. It could take less, but it's never going to take more than that. And so it's kind of like a barrier, like we know it's going to take this amount at the most. It's going to take this amount of time at the most. And so that's the same thing down here. Like we know it may not take this amount of time, but we have this upper bound saying it's not going to take over this amount of time. It could be equal, it could be less than, but it's not going to be greater. But can we improve this running time? Can we use the different data structures to create a more optimal solution, a faster solution? Well, we can. We can do public static int. Again, we'll do find num of repetitions v2. And can we spell things correctly? So we will copy and paste this guy down here. And we'll take again a string and a character. And we are going to use hash maps, our dictionaries, to make this running time be O(n) time. So our goal, we'll say optimal time is O(n) time, so linear time. So the size of our input is the same as the size of the solution. And so to do this, we're going to do the same type of sums thing up here. So we'll just copy and paste that down here, because we're going to want to return this int array no matter what. But instead of doing this double for loop thing and jumping right into it, we are going to use a data structure, which is going to take up more space, but it's going to allow us to do it in n time. And it's going to be a hash map like I was saying before. And so we'll do hash map, and it's going to map character to integer. And we will just call this map, and it's going to be a new hash map. And there we go. And so after this is initialized, we have to, of course, import things. And after that, we are going to use this single for loop. And of course, we'll start off at 0. And then we will go all the way up to the string.length. And we will do I++. And for each character inside of the string, we are going to add an entry to our hash map. And if we run into that character again, like we have a repetition of it, we're going to go and get that character from the hash map and then increment its value, its integer, by 1. And so we will say if the map dot contains key, and we will say the character string dot character at I. If it does not contain it, then we want to put it inside. And so if it does not contain it, then we want to do map.put key, and we are going to want to put this key, which is the character that we just grabbed, and we are going to want to put in 1 for that because we have 1 occurrence. Otherwise, if it contains the key, then we know the key is inside of our hash map. So we can just go and get that key, get its value, and then add 1 and put it back into that map and have its value be updated. And so we could say int sum, which is just going to be the map dot get object, which is the key. And so we'll go get the thing that is mapped to our character, and so it'll be 1, it'll be 5, but it will not be 0, and then we will put it back into and up into the map, and we will just say s.char at I, and then we will give it the sum plus 1 to increment its sum, and so we say there has been a repetition in this list, or really in this string. And so I did say this is going to be n time, but actually it's going to be n plus m time, because again, the string and the character array are not guaranteed to be equal in length. And so whichever is bigger, if the character array is bigger or if the string is bigger, that's going to be the dominant thing. And so say your character array is 25 long, your string is only 5 long, well then it's going to run like 25, milliseconds, because the character thing was bigger, which is fine, and that's going to be our most optimal thing we need to get here, because what this hash map does is it gets the occurrence of every single character inside of the string. Like if you have A, B, C, A, then it's going to get like, okay, A's have 2, B has 1, C has 1, done. But what if your character array asks for like Z? That's going to be 0. Or what if it doesn't ask for A? Well, you have it in your hash map. And so we need to kind of narrow it down into our specific specifications. And so to do this, we are going to have another for loop, but it's not going to be nested inside of this for loop. And so it's considered a completely different thing, and we don't have this end factor that we did up here. It's just going to start off straight from fresh. And so we will have j equals 0, while j is less than c dot length, and then we will do j plus plus. And so inside of this for loop, first we're going to create an in sum for each and every, character, and then we're going to ask if the character is inside of the hash map. So we will say map.contains key and c at j. And if it does not contain the key, then we will add our sums at j is going to be 0. Otherwise, we're going to go and get that value from the map, so we'll have an else, and we will say map.get our object, which is just going to be c at j. And so we're going to go get the value that how many repetitions has this character at c at j have, and we're going to put that sum inside of our sums at j. So either it was not in the hash map, meaning it was not in the list, or it was in the hash map and it was in the string, and we're going to add this repetitive value inside of our sums in the correct position. And we know that it goes from 0 to c dot length, and so this index should be fine. And then at the very end, of course, we need to return this sums array, and then we should be good to go. And of course, we need to add the 2 there because it's mad that I'm calling things the same thing. And so now we can actually, I'm going to copy and paste this so we can see what's up here. And we'll paste it here. And so we are just going to do that and that, and we are going to see how long these functions run on like the same input, or at least the last 2. The first one's just going to stay the same because it's already optimized, but our second one is now optimized as well. But I could of course tell you all the reasons why it's optimized, but I'd rather you just see it for yourself. So say you have this really long string. Okay. And so you have this long string, and we will copy it, and we will paste it down here as well. And then we will create an array called A, and we will add it inside of here. So we will go over here, we will say char array, and this is just going to be A, and it's going to be this thing. And inside of here, we need to say v1, and then we need to say v2. And so now let's see what happens. And so let's play. And notice the difference here. Our first thing only took 1 millisecond, which it has been doing. And then our second, the one that took n times m times, took 18 milliseconds. And then this thing, our last test, only took 8 milliseconds. This input isn't big enough to show a huge difference, but when you're starting to work with thousands and thousands of letters and strings and stuff, this is the stuff that really matters. Here it's only a millisecond difference, but like in the future when you work on really cool projects that impact lots of people, it's going to matter. And so this is really, really important to know. And I want you to really, really notice here and take note that by adding a data structure, adding something that took up space, allowed our program to run faster. See, before we were only using an array, now we use a hash map, and that's what made this faster. And so thinking of data structures that can optimize your code and make it run as fast as possible, That is the key to this whole thing. And so that's it for this video. The HackerRank challenge is down below in the description, and if you have any questions, feel free to leave a comment on this video. I hope you learned something, and I will see you tomorrow.